This lab nugget is going to challenge you to design a database utilizing all we've learned up to this point. So you'll walk through the process of normalizing a table into multiple related tables, create and configure your relationships utilizing foreign keys, and finally coming up with an indexing strategy for this database. Let's jump in. Welcome back to the Virtual Nugget Lab. Let's jump into SQL Server Management Studio, and we're going to be working with our project here called Lab Designing a Database. So try this lab out on your own, and I'll walk you through all the solutions and the answers to the questions here now. Now, the first thing you want to do is open up the setup.sql script and execute it. This is going to set up TestDB with a couple of tables here and get us ready to go for this lab. Once that's done, head in to our lab instructions. We'll start here with normalization. So if we take a look at our first task here, it says examine the table order underscore zero normal form and identify what is wrong with the current design. So let's expand databases here. Let's head into TestDB and expand tables. Now, if you don't see this table in here, just refresh it, and you should see that table after running setup.sql. So if we take a look at this table here, let's just look at the columns. We have an order ID, customer name, customer address, customer city, customer state. We've got products. We've got order information around the order, and then we've got order detail information. So just by looking at this table, you can kind of get an idea as to what we're working with here, right? We're going to need a products table, a customers table, an order table, and an order details table. Pretty standard design for any kind of retail database. And why would we want to break a table like this down into multiple tables? One big issue is, of course, data redundancy. Another are all the data anomalies that we would be dealing with for the lifetime of this database. Insert updates and deletes would be quite painful to deal with. All right, let's take a look at step number 2 here. Transform this design into third normal form by separating the columns into multiple tables. So 2-normalize.sql contains the solution here for this problem. Let's take a look. So here I've come up with 4 tables. We've got a customer table to track this customer information. We've got a customer ID. We need an identifier that's going to be the primary key for the customer. We break the name into first name and last name, and then we have address, city, and state for all those other fields. So this is our customer table, nice small focused table that tracks just customers and would get us away from all of those data redundancies and data anomalies. Next up, we have our product table. Notice here we've got some product columns in here, name, description, inventory, price. So we'll bring those over into this table and slap an ID on it that will allow us to uniquely identify all the data in that table. Heading down here, we've got our order table. So our order table is going to contain information about the actual order itself and tie it to the customer. So this is why we have things around the order. Remember, an order could contain many order items, right? A customer could order many products, all with different quantities and such. So that's why we have an order header table to track the order and the customer that it belongs to, as well as the order date and the ship date. And the order detail table will then tie the order to all of the products that customer ordered. That's why we have an order ID within here, as well as the product ID, the quantity they ordered, the price, and potentially a discount associated with it. And by the way, you'll often see price in multiple tables, right? You'll see it in the product table, which will usually be the base price of the product. The order detail table will have the price, which will take into account the discount as well as any taxes and that kind of thing. And then you may have a total price in your order table. All pretty common scenarios in databases like these. So let's go ahead and execute this script to create all of those tables. Let's head back into Object Explorer here. We'll give it a refresh, and we should see our now normalized design. Let's close out of this and head back to our lab instructions. And the big question for this lab challenge, what is the purpose of normalization? As we saw, it's there to get rid of redundancies and to get rid of data anomalies and make it far easier to develop against and manage down the road. Of course, our queries may get a little more complicated because we're going to have joins all over the place to bring all this data together, but it's a small price to pay for what other problems would pop up down the road. Our next lab challenge is going to have you configure the relationships between these tables. And our first task here is to configure the relationships using foreign key constraints. And this should be a fairly straightforward task if you designed your tables right and named your columns right, because you'll easily be able to see, for instance, our customer table has a customer ID, our order table has a customer ID, because we need to associate orders with customers. So this will just be a matter of placing a foreign key constraint on our customer ID column in our order table that references our primary key customer ID in our customer table. And you can actually see that here as well with our order detail table. We've got our product ID as well as our order ID. So we're going to need 3 foreign key constraints. 2 in our order detail table, one that's going to map order detail to their order, one that's going to map our order detail item to the product that was ordered. And if you feel comfortable doing this in the GUI, feel free to do so. Otherwise, the SQL is actually really easy, and you can find it here in relationships.sql. So if we open this up, we've got our 3 foreign key constraints. We just run an alter table, add constraint, give it a name, specify your foreign key, which in our order table is going to be customer ID. That's going to link to the customer ID in our customer table. Order detail, we have got 2 of them. One for product ID that references the product ID primary key in the product table, and one that references the order ID in the order table. So let's go ahead and execute this, and that'll create those foreign key constraints. Now, task number 2 is to view the relationships by creating a database diagram. So this will just be a matter of heading up to database diagrams, choose yes here at the dialog, right click, choose new database diagram, and add those tables in here. We'll take our 0 normal form table out of there. We'll hit add and hit close, and now because we created those foreign key constraints, it'll automatically show them inside of the diagram. So now we can get a visual of how all of our data is related together. Our third task here is going to have us modify the order to order detailer relationship to add a rule for cascade deletes. In other words, if we delete an order record, we want to delete all of those order line items with it. Because as it stands right now, if we were to try to delete an order because of referential integrity, we would get an error. All right, so you can do this in SQL just by recreating the foreign key constraint and adding those rules onto it, or the easy way here is to do it through the UI. And you can do it through Object Explorer, or you can go into your database diagram, identify that relationship. Here it is right here, our relationship between order and order detail. Right click, choose properties. That'll pop it up over here. And so this will just show us that this is the right one, right? We've got our order table is our primary key, and our foreign key is order detail, meaning if we were to delete an order, we want it to cascade down through the foreign key and delete all of those order details. So if we head down to insert and update specifications here in the properties window, here are our rules. So on the delete rule, if we drop this down and choose cascade and save it, it's going to click right in the white space here and hit save. Type in a name for our diagram, relationships, hit OK. Here's the dialog that shows us that's going to change what we just made here between these 2 tables, our foreign key. We'll say yes, and now we have cascade deletes turned on. So if we were to delete an order item, all those order details would go with it. Let's answer some questions here. What does a foreign key constraint accomplish? I just said it a little bit ago, referential integrity. It ensures that our data lines up between the tables. So we can't put data in our foreign key table that doesn't have a match in the primary key table, nor can we delete things or change things in our primary key table that would affect our foreign key table. Next question, what kind of a relationship do we have between order and order details? Well, we can head back to our database diagram and take a peek. We can see here that we have an order on the one side and an order detail on the many side. This is a one-to-many relationship, meaning we're going to have one order that's going to be associated with potentially many order details. Our final question here, what is the difference between cascade and set null on a foreign key constraint? Those rules that we can apply to a foreign key constraint. We can do it on delete and we can do it on update. Cascade means that it will, anything we change in the parent table will cascade to the child table or through our foreign key constraint. Set null means it will set our child null. So if we have a delete rule on our order table and we delete an order and we have set null on, it's going to go and nullify all of those child records in the foreign key table rather than delete them. So cascade means it'll cascade that action, so either a delete or an update. Set null means it'll nullify them, which will leave us with orphan records, but it won't destroy the data. So we can still see the data if we need to keep it around. And then, of course, we can use outer joins to find that data. Let's move on to our last lab challenge, which is going to be working with indexes. Our first task here is to create a non-clustered index on the product table for the price column. So let's take a look at that table. And you know what? Let's say that we've got a website on top of our database. And we've identified one of the more popular queries to hit our server is against that product table and specifically against the price column. Maybe we've got a page where customers can search for products and one of the more popular filters is that price filter. So we want to make this as efficient as possible. We've noticed that query has been slowing down over time and we also notice there's no index on it. So a great way to speed this up instantaneously would be to simply put an index for those range searches on the price column in this table. Let's do it. Let's head over here to Object Explorer. Let's open up /indexes.sql, and here it is. It's as simple as this. Now, there's a number of ways that we can put indexes on these tables. You can use the GUI. You can use the designer when you're in the table designer. Lots of ways to do it. But the SQL way, of course, is a great way to learn because you can easily type out some SQL here to create these indexes at will. So here is our first index. We're going to create a non-clustered index called IX underscore product price on our product table for the price column sorted ascending. So let's go ahead and highlight that and hit execute. And there we go. We created an index. Let's head back here to our lab instructions and take a look at our second one. Our second one is to create a non-clustered index on the order table for the order date and ship date columns. So here, let's say that our customer service team started complaining that their queries were slowing down. We've identified that whenever they do troubleshooting for customer orders, they often query for the order date and ship date columns. So what we can do then is create what's called a composite index, right? An index that contains multiple columns. We'll say we've identified there's a lot of queries that have order date and ship date in the where clause, and so this will dramatically speed up any of those queries. And if we head over to our indexes.sql script once again here it is. Create non-clustered index, give it a name on our table, and here we're specifying multiple columns rather than just a single column. So if we hit execute, that will create it. And now our third task is to view the indexes on these tables in Object Explorer. Easy enough, we can find both of these indexes underneath their respective table. Just expand indexes. You may need to refresh since we did this in SQL and we already had Object Explorer open. And once you refresh it, you will see those indexes. There is our product price index, and if we expand order indexes, there it is. You can go into the properties of those and look at the details of those indexes, but that would dramatically speed up both of those queries in that case. Let's finish up with some questions here. What is the purpose of an index? Yeah, performance, right? Purely there to speed up the performance of queries that utilize an index. Question number 2, what is the difference between a clustered and a non-clustered index? Remember, a clustered index physically stores table data in the index, and a non-clustered index stores that data in a separate structure that then references either the clustered index or just all of the data inside of the data pages underneath SQL Server. The last one here, which index type can you have more than one of on a table? And the answer to that is the non-clustered index, because it is a separate structure. You can only have one clustered index on a table because that clustered index becomes storage for the table. And that's our lab on designing databases. That's a lot of what you'll be doing when you design a database, right? Identifying your data points, normalizing them into tables, creating relationships, and then creating your initial indexing strategy. In the CBT Lab Nugget, we saw how to design a database, from normalization to configuring relationships and 4 key constraints to creating indexes. I hope this has been informative for you, and I'd like to thank you for viewing.